Great. So our next speaker is David Jones. Sorry? What time is it? Oh, okay.
Just feeling really prepared.
Yeah. Okay, you can wait 3 minutes more. Sorry. Yeah.
Certain of these slides are stolen from Patrick's talk, who's talking right after me. Oh, nice. It's much better than the one that I made that also shows the fields.
Okay, now we're in time. Sorry for that. 2 minutes of silence. Our next speaker is David Jones. He's an Einstein Fellow. You're in Santa Cruz, right?
Yep.
Yeah, great. He's going to talk about the Young Supernova Experiment. So take it away. Thank you.
Awesome. Thank you so much to the organizers in Gotham. It's so nice to see everybody in person, meet collaborators who I've never met in person before as well, and just awesome to be here. And there are a ton of members of the Young Supernova Experiment here this week as well. Maybe we can get dinner tonight for those who are around. You heard it here first. I'll say it on Slack. Yeah, I wanted to talk about some early results. This is a new time domain survey on the Pan-STARRS telescopes and what we can do for the LSST Rubin Observatory community. This is, by way of introduction, the log-scale number of supernova discoveries for the last 100 years or so. Didn't realize until I made this plot that there weren't many supernovae discovered during the Great Depression or World War II, which I guess makes sense in hindsight, and then things kind of leveled out for a little bit. And then we had the discovery of 1987A, cosmic acceleration. Things started to pick up, the Sloan Digital Sky Survey, Pan-STARRS, and then all these new surveys like ZTF, Assassin, Atlas, and the rate of transient discovery is just continuing to increase exponentially, and the Rubin Observatory will increase this discovery rate by another order of magnitude. And so with that discovery rate comes a fantastic opportunity to learn more about transient physics. This is kind of the classic plot from Manzi's thesis that just shows the peak luminosity versus timescale for lots of different classes of transients. So this wealth of data will give us a chance to fill in regions of this plot, timescales and luminosities that have barely or never been explored before, as well as just increasing the amount of data in each of these categories by orders of magnitude. And in addition, I've done most of my work on supernova cosmology, so I wanted to kind of show the current landscape versus what we'll have for LSST for cosmological measurements, which includes, as people were talking about yesterday, measurements of the Hubble constant, subject of a 5 sigma tension between predictions from the early universe. In addition, there's some interesting tension, primarily from galaxy surveys with the growth of structure parameter F sigma 8. Supernovae, especially at kind of low-ish redshifts, can make measurements of this tension as well, which is extremely interesting. From supernovae, this is a 1.7 sigma difference between supernovae and the CMB, which is not really tension. But I know the galaxy community is taking this really seriously, and the implications that it might have for gravity or other potential new physics. And then dark energy, we have in sum total about, I think, more like 1,500 type 1a supernovae in Pantheon Plus analysis, which I'm sure Dylan will talk about on Friday, out to approximately redshift 1. There are a few beyond redshift 1, but not too many. But we're about to enter the Rubin Observatory era. None of these measurements are systematics dominated yet, so it's a fantastic opportunity to increase the sample size by 1 to 2 orders of magnitude with more than 100,000 type 1a supernovae out to redshift 1 from the Rubin Observatory. And I think Ben's Roman reference survey document says there will be about 10,000 type 1a supernovae likely out to redshift 2 from the Roman Space Telescope as well. So this enormous amount of data, we're going to hear about it all this week, presents all kinds of challenges for classification and follow-up. We need brokers, target and observation managers. I'm sorry if I forgot anybody's talks here. And where the Young Supernova Experiment, I think, comes in is that it helps to have real existing survey data to prepare for the data stream that Rubin will give us. And so Young Supernova Experiment is not a unique source of transient data in the last couple of years, but what is kind of unique is the Pan-STARRS telescope, which is a relatively small telescope with, I think, like a 1.4 gigapixel camera. It's discovered more than 30,000 transients, which according to TNS is the largest source of transient discoveries. I think from Mark's talk yesterday, ZTF has 28,000, so they may soon surpass Pan-STARRS. But for now, and then Pan-STARRS also has GRIZ-Y filters. Most transients haven't been observed in Y-band, but lots in GRI and Z, so the same as LSST, except for the fact that LSST has a U-band filter. Pan-STARRS has observed transients from redshifts of 0 to about 0.7. So it's really the telescope with the most similar capabilities to Rubin of any existing facility. And these data have had huge impacts on supernova classification, supernova cosmology, supernova physics, and there are just way too many individual papers to cite here. But this is one example in this figure here of foundation supernova survey data that I worked on with Armin and Dan Skolnick and Ryan Foley, and these are just a bunch of GRIZ light curves for low Z type 1a supernovae observed through that survey. So realizing that Pan-STARRS is this really special facility, a couple years ago we embarked on the Young Supernova Experiment, which is a supernova discovery survey with Pan-STARRS for transient astrophysics and cosmological parameter measurements. Importantly, this is our survey logo from Matt Siebert with YSE spelled out on the CCD chip. The survey has 7% of the time on each of the Pan-STARRS telescopes, modulo some telescope downtime, of which there's been quite a bit, but I think, I've said this before, but I think in the next like 2-3 weeks we'll actually be observing on both Pan-STARRS telescopes, go from covering 750 square degrees on the sky with a 3-day cadence to 1,500 square degrees. And the really nice thing about being a transient astronomer today is that we have, if you start a survey like EASY, you also have data overlap with ZTF and Atlas. We have a long-term DECam survey headed up by Armin, which is just like a great chance to both get a higher combined cadence and have this really beautiful like synthesis of data across different surveys and telescopes. And this is just a figure of our fields on the sky to date, or I guess circa 2021, and we'll double those soon. The survey wouldn't be possible without a huge team. Particularly, there are a lot of people here at this conference. These are, hopefully I didn't miss any. These are everybody giving talks at this conference, and shout out to the local Illinois PIs, Decker and Gotham, and our executive committee. We have like 130 people. We used to have a high schooler, but Armin's daughter graduated, so congrats. So now just undergrads, grad students, postdocs, faculty, and research scientists. And we've discovered a little over 3,000 transients, discovered or observed a little over 3,000 transients to date. So we're observing transients at a rate of about 5% of those being discovered in astronomy right now. And as I mentioned, we're about to double our area, so lots more discoveries to come. And we're kind of targeted at the redshift range of 0 to 0.2, a few things up to redshifts of 0.3, and that lower redshift range has allowed us to get lots of supernova classifications. So we have nearly 600 classified transients to date. So in 2 years, we have more transients classified than the Pan-STARRS Medium Deep Survey had in 4. Primarily, of course, because of the efforts of the community and the lower redshift nature of the data. So I wanted to just kind of talk through some of the early science results and then say what the Young Supernova Experiment can offer the LSST community. So our science is focused on a number of topics. First and foremost, young supernovae. So we have a couple papers out on core collapse supernova flash ionization, where the supernova after shock breakout ionizes the circumstellar medium that was shed by the star in the last few years of its life, and you get these beautiful narrow flash ionization lines. These are Keck spectra from Giacomo Terrerin and Wynne Jacobson Glan's papers. We also have the first and I think only to date Hubble Space Telescope ultra rapid target of opportunity observation where we observed supernova 2020 FQV within I think 3 days after its explosion, and then messed up the HST schedule for everybody else for the next couple weeks. And Alex has a paper as well on really early observations of type 1c supernova 20OI with an early excess emission. We have only one paper to date on young type 1a supernova, but we have a number of interesting objects, so I hope we get more soon. This is from Yorgos Dimitriadis on a Super-Chandrasekhar type 1a supernova 2020 ESM that was observed very early on in its evolution and appeared to have a carbon-oxygen atmosphere. And then a really nice paper on supernova progenitors, and another one coming soon from Charlie Kilpatrick, where Charlie identified a type 1b supernova progenitor candidate in archival HST imaging a couple years before explosion. This is one of a very few known type 1b progenitor candidates, and I think is our most cited paper to date. And I'm really excited. Hopefully this will be on the archive soon. I think it's nearly accepted. This is the discovery of an intermediate mass black hole disrupted tidal disruption event candidate from Charlotte Angus. These are just M sigma diagrams where this is the object, and I think this just goes to show the way in which tidal disruption events can potentially probe the demographics of black holes in the universe. And Nick Earl will give a talk on another really well-observed tidal disruption event in Yeezy in maybe tomorrow or Thursday, I forget exactly. And last but not least, we're very interested in supernova cosmology, and we have cosmological results in preparation. And particularly, there's a new Hubble constant analysis from Sam Ward that Sam will talk about on Friday using a Cepheid galaxy with 3 type 1a supernovae. We unblinded yesterday. I won't spoil anything, but Sam will tell you what the results of that were on Friday. So, okay, so it's always, of course, good to learn about supernova physics and cosmology, but what can we offer the LSST community? First off, brokers, marshals, target observation managers. I guess first and foremost, all of us are kind of acquiring quite a bit of domain knowledge on the complex interactions between various brokers and data streams. So this is just like a complicated figure of how Young Supernova Experiment data gets to us, starting from University of Hawaii, IPP, Queen's Belfast, UC Santa Cruz, interacting along the way with the Transient Name Server, Antares, ZTF. We also have just like quick drag and drop requests through LCO and also SOAR, so thank you for an amazing API. It's really, really easy. Anybody can just request follow-up photometry anytime they want. And in particular, this last stage of the process is a web application that we built at UC Santa Cruz for follow-up and data synthesis and triage. So this is called Easy Peasy. Dave Coulter has a paper on this in preparation. It's already a Dockerized, fully public code and database, so I hope people find it useful, and hopefully we've provided some interesting features that can be incorporated in other Marshalls and Tom systems. And our version housed at UCSC has 75 monthly active users when I checked a couple days ago. We're actively developing. We have some host galaxy characterization improvements. And it's a really nice system. If anyone would like to be involved or part of this group of 75 people that are using it right now, please let me know. It starts with kind of a dashboard system where new transients come in. Then we have transient data and metadata with interactive plots of spectra and photometry and everything we can synthesize from ZTF, Atlas, other sources. We have all of our observing nights where we collect the requests for follow-up that people on the team have provided. And then everything is built on top of a SQL backend, so we can query on anything in the database, which is not just the 3,000 Yeezy transients, but the 100,000 odd transients we've ingested from TNS since late 2017. In addition, this is a really great opportunity to use real data to vet classification tools, and so Patrick's talk is really going to focus on this, so I'll spoil a little bit of Patrick's talk, but hopefully not too much. It's obviously important to find exciting objects in samples of tens or hundreds of thousands, and we also need to understand how the contamination of type 1a supernova samples affects the measurement of cosmological parameters. And it's really nice to have real GRIZ data on which to develop these kinds of tools. Ashley Villar did great work on the medium deep survey, and now we have additional data at lower redshift with more classifications from YSZ. And so one of the things I just wanted to highlight from Patrick's in preparation paper is that when you have real data, you find some things that you might not expect. And this includes, these are kind of ugly light curve plots, so sorry about that, but we misclassified Super Chandrasekhar type 1a supernova. We had things like a nuclear type 1a supernova with really red colors and kind of a crazy light curve. We had a misclassified luminous blue variable star, another Super Chandrasekhar type 1a supernova, a double-peaked type 2n supernova that we're not quite sure what's going on, and we're looking at this. There was a type 1a supernova with a weird linear rise and decline. It kind of looks like a transitional type 1a, but the luminosity is just normal for a type 1a supernova, and it has kind of an early time blue bump, so this is really interesting. And then things like type 1ax supernovae that were also being misclassified. So I guess I wrote, it seems like nature is weirder than simulations predict. I'm actually not sure about that because Plastic had cosmic strings in the simulated data set. But the other cool thing about this is it's a great time to be a transient astronomer because Yeezy, ZTF, Atlas, DECam, other surveys are just an incredibly rich combined data set for this type of science and transient characterization. So Patrick will talk about that more, but also Patrick is releasing our DR1 from the first 2 years of the survey, which will include 2,000 supernova light curves with ZTF and other archival data potentially, and 300 or so supernovae in our magnitude and volume limited sample. So definitely our discoveries are in order of magnitude below things like ZTF, but I think the nature of pan-stars makes it a unique data set as well as the synthesis with other surveys. And then last but not least, we're excited about having a low Z type 1a supernova sample for cosmology. At a bare minimum, the Young Supernova Experiment will provide another calibration system to anchor the type 1a supernova Hubble diagram. Depending on what happens with the Rubin cadence, it might also be able to supplement those data and make the most of the next generation of cosmological measurements. And so this is our preliminary Hubble diagram. The scatter is a bit large. We're still working on a redshift survey. But comparing to the Pantheon analysis from 1990 to 2010, there were about 400 supernovae at redshift less than 0.2. In just 2 years of YSE, we have about 400 supernovae already, and that's just with 50% of our eventual survey area. So stay tuned for that as well. And I'll just end by saying I think this is one of the best surveys to prepare for Rubin Observatory data. thank everyone in the room who's collaborated on YSE and done so much of this work to keep the survey running. And we're always looking for new collaborators, both external and full members, getting cheaper every day. And if you're interested in more details about the survey, come talk to me, and there's a paper on the archive. Thanks.
Thank you so much. Questions around? Here. Okay. You have a question?
Thank you for the talk. Actually, probably this is a question for Nick, but I saw some of the plots where there were like photometric classifiers for type 2s. Were they characterized, or like were they just classifiers?
Let's see, was that this one?
Yes, that's correct. So I saw those.
So really, well, I guess I'll say these are, I think, from Kyle Boone's parsnip classifier.
Yeah.
And I think these are all successful classifications. Patrick is going to give, I assume, most of your talk, Patrick, on classification. So I'll mostly just leave that to Patrick's talk. But yeah, it's, Patrick is exploring like all of these nuances, and it's difficult when you move from simulations to real data and think about training sets and differences between the training set and the real set. And yeah, anyways, it's been hard work, but we're about there.
Yeah, thank you. I look forward to the talk.
Okay, there's a comment in Slack, in the Zoom chat from Rick saying that plastic did not have cosmic strings because they never satisfied 2 detection trigger. Yeah.
Too bad, so close.
Going with the joke. More questions? We have time for one more. Can you show that last plot? I want to see the redshift range.
Oh, sorry, yeah. I think this is photo Z bias at the very end if you're like thinking of the kind of artifact here above redshift 0.2. I don't, Malmquist bias isn't that big for type 1As.
Okay, so do you know how many supernovae are below 0.1? What's the number?
Below 0.1, I think it's at least a couple hundred.
A couple. Is it in the hundreds?
Yeah, because most of our classifications of 1As are below 0.1, and I know we have like 300 classified 1As. But looking at this Hubble diagram, it looks more like, I don't know, 100, 150.
Okay, thank you.
Yeah, so that's obviously a really valuable sample, though in particular with like recent work on peculiar velocity uncertainties.
Right.
I'm thinking like the ideal is actually like 0.05 to 0.1 or something.
Exactly, yeah. Okay, thank you.
I was just going to say again quickly, we have plans to do a lot more kind of targeted follow-up of some of these lowest redshift supernovae, and we haven't done as much as we'd like to.
Okay, thank you.